In this lecture, we will be looking at the direct comparison test for divergence for infinite series. So this is very similar to the direct comparison test for convergence that we previously covered. We just reverse the situation. So roughly speaking, we have a series of all non-negative terms, and the idea is we're given a series and we're going to find a simpler series that's both smaller and divergent. If it's smaller and divergent, the bigger one has to be divergent as well. So consider a series, think of it as the one you're given. The sum n goes from 1 to infinity of a sub n. All the a sub n are non-negative. And suppose there exists a divergent series. Sum n goes from 1 to infinity of L sub n. So we're using L for lower. So the idea is that L sub n is below a sub n, starting at some point and holding that inequality thereafter. So at some integer capital N from there on, you have this inequality. Well, that means you have found a smaller divergent series. Since the one you have is bigger, it must also diverge. Put another way, the given series of a sub n dominates the smaller series of these lower terms, L sub n. And summarized here, your series going from n equals capital N to infinity of these L sub n's, these lower terms, we're saying that that's a divergent series, so it's infinite, and our series is bigger. And again, we're having this start at capital N here because we're saying that's the index at which this inequality begins. Most of the time, we're going to actually see n equals 1. Usually right off the bat, you will have your inequality. So what you have to do when you use this test is look at the series and try and get a sense. Do you think it converges? Do you think it diverges? If you think it diverges, you are on a quest to find a simpler, smaller divergent series. If we illustrate this, we can think of each of these series as a sum of areas. And so our given series, A1, A2, A3, so we're just creating a visual depiction of what we mean by adding up our a sub n's, and we'll think of it as this orange area. And so that area we think of as the sum n goes from 1 to infinity of a sub n. And again, we will be claiming here that starting with all n greater than or equal to 1, so that's the case where our capital N is 1, we have our a sub n dominating what we're calling our L sub n. We're saying lower. So now if we depict these L sub n's, they'll be smaller. So they'll be L1, L2, L3, L4, so on and so forth. And the idea now is if we look at this shaded region, that represents the sum n going from 1 to infinity of L sub n. And we're saying this is infinite. So when you add up these purple areas and you get something infinite, well, our given series is the sum of these orange areas which is bigger. So it also has to be infinite. The direct comparison test for divergence can only be used to conclude that a series diverges. So you're on the quest for a smaller divergent series. For example, suppose we have this here. The sum, and we know n has to start at 3 because we have to avoid division by 0. You can't have a natural log of 1, which is 0, in the denominator. And we look at this, and this one can be tough to have intuition for. But if we think of natural log and we think about the graph of natural log, we know it looks something like this. But if we draw the 45-degree line, which is y equals x, and think about the comparison here, n if n is 1, natural log is smaller than n. So natural log 1 is smaller than 1. Natural log 2, smaller than 2. Natural log 3, smaller than 3. So natural log of x is smaller than x for all x positive. Well, what that means intuitively is natural log x is going to infinity more slowly than x. So natural log of n goes to infinity more slowly than n goes to infinity. Just tracing along these graphs here and knowing that if you evaluate these at the counting numbers, which are along for the ride, that just means natural log n is taking its sweet time to get to infinity when compared to n. Well, that means we have a denominator. This natural log term is going to infinity very slowly. Natural log of it will actually slow it down even more. So we have a denominator that's really taking its time going to infinity, which means this sum end, right? If the denominator is going to infinity slowly, the fraction itself is going to 0 slowly. And remember, what's the fundamental question we're always trying to answer when we look at a series? Do the terms go to 0 fast enough such that the series is finite? And our guess here is going to be no, that these terms are, because the denominator is just going to go to infinity too slowly, these terms are probably not going to 0 fast enough. So if we suspect, our series diverges. And if we suspect our series diverges, and we don't really know what to use for a comparison, it's often worth trying the classic divergent series or the harmonic series. So let's try comparing to the sum n equals 3 to infinity of 1 over n, again, called the harmonic, which we know diverges. So let's do some comparisons. First, from our depiction here, we know that for n greater than 0, natural log of n is less than n. Right? We've depicted this here. So natural log of n, we have being these points, and n equals n you can think of as happening here. And we see n is bigger than natural log of n. Because the natural log is an increasing function, so because natural log of x is increasing, we can take logs of both sides. And maintain the inequality. So the natural log of natural log n is less than the natural log of n. So all we've done is take natural log of both sides here. But notice now we can string these together. This tells us the natural log of the natural log of n is less than the natural log of n. That's this inequality. But the natural log of n, go up here, is smaller than n. So now, with these inequalities, we can now realize that we don't care about the middle. What we care about is that the natural log of the natural log of n is less than n. And notice what we've done. Here we have the denominator from our series. Here we have the denominator from the harmonic. So if we cross multiply, we have that 1 over natural log of n is greater than or equal to 1 over n. And remember, our sum started at n equals 3. So again, our given series was this here. So with the inequalities we just built, we saw that our series has to be bigger than or equal to the series where we sum 1 over n, simply because we have this inequality. But that sum, n goes from 3 to infinity of 1 over n, is infinite. And again, that's because the harmonic series diverges, which we showed in an earlier lecture. So we found a smaller divergent series. That means this also has to be infinite. The series we have is bigger than this series, which is infinite. And so we can conclude that the sum, n goes from 3 to infinity, of 1 over the natural log of natural log n diverges by direct comparison. To look at another example, suppose we have the sum n going from 1 to infinity of 1 plus sine squared n over n. And again, we want to get a feel for these and try and guess if it converges or diverges. And when we look at this, we see we have n in the denominator. That should make us think again of the harmonic. So in the numerator we have a 1, but then we know we're adding this sine squared n term, and we know that sine squared n is just some term bouncing in between 0 and 1. So we can say this is 1, each term is 1 plus some change, but that change is never really adding up to anything. So this is going to behave a lot like the sum of 1 over n. And specifically, let's try and build an inequality that gets our summand here compared to the harmonic. So we see here we want a sine squared n plus 1, so let's add 1, and we get 1 less than or equal to 1 plus sine squared n less than or equal to 2. And n is always going to be greater than 0, so we can divide each term by n and maintain the inequalities. And we see here that now in the middle we have our given series. And the question becomes, which of these do we use? So we have our term. We have it being less than or equal to 2 over n, or greater than or equal to 1 over n. But recall, we are thinking this series diverges. So we have to pick the smaller one. So this is the one that we want. So since the sum from n equals 1 to infinity of 1 over n diverges, again, it's the harmonic series, and one over n is always less than or equal to 1 plus sine squared n over n. We have found a sum of terms that is infinite, but each term is smaller than our given term. Our series is bigger. Well, you can't be bigger than infinity, so you have to be infinity. So we have the sum from n equals 1 to infinity of 1 plus sine squared of n over n, diverging by direct comparison. And so this illustrates how you use the direct comparison test. And again, you have to guess right for it to work. And one of the reasons I like to do these examples when we look at using this test for divergence with the harmonic is, if you're working on a series problem and you're really stuck and you can't tell, and you need a last resort, try comparison with the harmonic. Because sometimes it can be tricky to get a feel for whether or not a series converges or diverges. If you think it diverges, the harmonic is something good to try for direct comparison. This would be a perfect example. Example 1 here, people would generally find this to be a challenging problem. And so it's natural to try it. Try it with comparison for the harmonic. So this is a nice test. This is a intuitive test. Compared to many of the other tests, it's more intuitive because you can think of it this way. You're given this orange and you find purple that's smaller, but the smaller is infinite.